We're going to talk about 4 things that can happen when you heat an object. Thing number 1, its temperature will rise. Thing number 2, it can expand or contract. Thing number 3, it can change phase. Thing number 4, it can glow. What we have here is 2 cups. One cup is filled with vegetable oil. The other cup is filled with water. And in the middle, I have a beaker filled with boiling water. Now, in this boiling water, I have 2 cubes made of brass. They're cubes, they're about 1 inch long, same size. So both the cubes and the water, since they've been here for a while, should both be at 100 degrees Celsius because the water's boiling. So what I'm going to do is I'm going to move the cubes. I'm going to move 1 cube into the mineral or the vegetable oil, 1 cube into the water, and we're going to see what happens to the temperatures over time. Okay, here we have the curve of my temperature as a function of time. The blue curve is my vegetable oil. The red curve is my water. And we can see the first thing I did is I took the cap off the water, took the thermometer out, put it back in. You can see that red curve tracing up. The water gets fairly hot. It reaches about 33 degrees. Same thing for my blue curve. You can see at this point I take out the thermometer, put the hot brass in, put the thermometer back in, and then the temperature starts to rise. In the beginning it takes a little while for the system to reach equilibrium. This is why you've got those weird humps there. But eventually you can see that the oil gets to a higher temperature, about 40 degrees, than the water, which is about 33 degrees. Heat capacity is quite literally an object's capacity for storing heat. If something has more capacity for storing heat, that means that I can dump a lot of heat in and not have the temperature change. Why? Because it has a lot of capacity for storing that heat. However, if I have a low heat capacity, I have a limited capacity for storing that heat, then even if I add a small amount of heat to my system, the temperature is going to increase substantially because there's nowhere to put that heat. It does not have a high capacity for storing heat, therefore the temperature is going to go up. Now, how can I express that mathematically? Well, what's certainly true is that if I add heat, we would expect the temperature to increase. So I should get a change in the temperature. My capacity for storing heat tells me how much that temperature is going to change. So we will use the symbol big C. This is going to be our heat capacity. Let's see if that works. Let's say I have 2 systems, like we did in our experiment. Let's say I add the same amount of heat, but there's different heat capacities. In one case, my heat capacity is small. Represent small with the down arrow. Well, that means if I have the same amount of heat coming in, I need a big temperature change to compensate. One goes down, the other one's got to go up. If I have a small heat capacity, nowhere to put the heat, I've got to increase the temperature accordingly. Similarly, I have a big heat capacity. Well, now all of a sudden, delta T doesn't have to be as large. It can be smaller. So for the same amount of heat, this doesn't change. For the same amount of heat, if this goes up, this has to come down. Or putting that into words, if I have a big capacity to store heat, I can dump a lot of heat in, not have a big temperature change. Here's another consideration. I've got 50 mils of water here, I've got 500 mils of water here. Which of these is going to be harder to heat up? Well, here I have 10 times as much water, 10 times as many water molecules. Each of those water molecules needs a certain amount of heat. So this should be 10 times harder to heat up. Or another way to put that is to say I need 10 times as much heat to heat this up, an equivalent amount as I would for this guy. So we want a way to distinguish between these two situations, even though they're both made of water. Certain materials might heat up more easily than others, but what's certainly true is that the same material, if I have more of it, will require more heat to raise the temperature an equivalent amount. To disconnect the amount of material from the type of material, we have another quantity we want to introduce. This quantity is called the specific heat. So here, I add heat in, I have a certain capacity for storing the heat, and then I get a temperature change. Well, now I want to do the same thing, but now I want to break apart how much material I have from the type of material I have. So the way to do that is, again, say you're going to get a certain amount of heat that you're adding in. Some amount of heat that we're adding in. I want to say, if I have a certain material, it's going to have a certain heat that it's going to flow for a given unit amount. So here we call this our specific heat. Specific heat, because it's specific to a certain material. If I have more of that material, it's going to take more energy to heat it up by a certain amount, so I'm going to put the mass in here. More mass is going to mean more material, therefore it's going to take more energy to heat up. And then again I get my temperature change. So we have these two quantities. We have specific heat, which depends just on the material. And we have heat capacity, which depends not only on the type of material, but how much material there is. We can write this nice relationship between the heat capacity and the specific heat. If we just compare these two equations, we can see that the heat capacity, big C, is equal to the mass that I have times the specific heat for that material. Now if I want to work out the units for this, just looking here, I know Q is in joules, because it's an energy. Delta T is in Kelvin because it's a temperature. Therefore the units of specific heat, or excuse me, units of heat capacity are just going to be joules per Kelvin. And then taking that over here, I can see that the units of specific heat are going to be joules per Kelvin, but now per kilogram as well. Joules per Kelvin per kilogram. So, back to our oil and water experiment. Why did the oil heat up more than the water? Well, if I look at the specific heat values for oil and water, I see that oil is about 1.67 kilojoules per kilogram per Kelvin. And I see that water is about 4.19 kilojoules per kilogram per Kelvin, which means that water has a bigger capacity for storing heat. What that means is that my water can absorb more heat without its temperature rising as much as my oil will. The oil has a lower specific heat, about 3 times lower, 2 to 3 times lower. So when it absorbs heat, its temperature is going to raise more than water's would for an equivalent amount of heat. The next thing that can happen when you heat an object is called thermal expansion. So I have here a ball and a ring. And as you can see, the ball barely fits through the ring. We're going to see what happens when I heat this ball up using a Bunsen burner. Bunsen burner here. I'm going to just connect this to the gas. Let's just turn that on. You can hear the gas going. I'm just going to light this up. And we can start to see our Bunsen burner flame going there. Just adjust that a little bit. Get a nice blue flame going on there. So I'm going to just heat this up in here, kind of like I'm toasting a marshmallow. Just leave that in there for a few seconds. Now you can see when I try to fit it through the ring, it will not go through. So it doesn't matter how hard I push either. What's happened is the ball is expanded. Generally, when you heat something up, usually it expands. Some materials contract. I'm going to just turn this down. Some materials contract, but for the most part, when you heat an object, it'll expand. If I give this a little while to cool off, eventually it'll just go back down to its normal size and it will start to fit through again. Now, let's try that again, but this time, what do you think is going to happen when I heat the ring? So the ring is going to expand as well, but is it going to expand inward, making the hole smaller, so it can't fit through, so the ball doesn't have space to fit through anymore? Or is it going to push outward and have the ring get bigger so that the ball fits through even easier? Let's try that. Heating up my ring now. You can see, as I try to go through now, it fits through very easily. See if you can figure out why it fits through easily when I heat the ring, but not the ball. Here we go. I have some object. I'm going to call its length L. Actually, I'm going to call it L0 for the original length. And we're going to heat this object up. We're going to change its temperature. And what we will find is that as I change its temperature, it is going to start to expand. It's going to expand by some amount that I'm going to call delta L. So how does this work? Well, let's see. I'm going to increase the temperature, and that is going to result in an increased length. So I am going to have some percent increase in length. And that's going to be proportional to my change in temperature. I can write the percent increase in length by just taking the delta L over the L0. This will give me how much, my length increases. That's got to be proportional to the change in temperature, which I write as just delta T. Now, different materials are going to expand at different rates. So for the same change in temperature, some material is going to expand a whole bunch. Other material might not expand very much at all. To determine how much exactly the length is going to change, we have this constant right here. That depends on the material that I'm working with. This is called my thermal expansion coefficient. Looking at this, I can see I've got delta L over L0, I've got delta T over here. Here my units cancel out, both on top and on bottom. I need to have no units on this side, so alpha must have units of 1 over Kelvin. Rather than expressing the percentage change in length, sometimes people prefer to express the percentage change in the volume. We get a similar equation. Looks pretty much the same, except instead of L, I'm just writing it in terms of the volume. Instead of I should say that this is the linear thermal expansion coefficient. I get the same thing, but now I just changed the constant. I used the Greek letter beta. And it's just the percentage volume change is equal to another thermal expansion coefficient times the change in the temperature again. It's just a thermal expansion coefficient. Box this guy up. So you can either look at changes in length or changes in volume as a function of the temperature. So, how do phase changes work? Well, let's say we were making a graph of the temperature of some piece of matter as a function of the amount of heat that I add to it. Let's say we start off at a low temperature, where it's in the solid phase, we're going to add some heat to it. Well, for the most part, I add heat, temperature rises, but then I get to a particular point right here. What I find is that the temperature starts to level out. I add heat in, don't get any change in temperature. This is usually a sign that a phase change is occurring. So I'm just going to box this off. And let's pretend that we're doing this for water. Well, for water, I know I get a phase change from solid to liquid, from ice to regular liquid water at 0 degrees Celsius. So I'm just going to put this down as 0 degrees. So here we would have had a solid phase. Here we would have had a combination of solid and liquid undergoing the phase change. Once it's all liquid, then all of a sudden I get my rise again in the temperature. Until again, my system starts to level out, my temperature starts to level out. I'm adding more heat but not getting any temperature change. Well, in that case, I've gone from a liquid, undergoing another phase change. This time, I get a mixture of liquid and gas. For water, that happens at 100 degrees Celsius. Now, those temperatures will be different for different materials. So if I used ethanol instead of water, I wouldn't get 0 degrees and 100 degrees. They would freeze and boil at different temperatures. But the same general trend would be true. I would go from a solid to a liquid, and then eventually I would reach my gas phase, and my temperature would start to rise again. Now, mathematically, how do we want to describe this? Well, if I look here, there's a region where I added energy, and essentially that energy didn't change the temperature. All it did was convert the solid to a liquid. Same thing over here. I add this much energy. That much energy here, that much energy here. In general, I'm going to have to add different amounts of energy for different phase changes. So here, I can describe a phase change by using this thing called the latent heat. So this is the amount of heat that I have to add to undergo a phase change. And it's going to depend on the amount of matter I have in my system. So if I am trying to boil a cup of water, that's going to take less energy than boiling an entire pool of water. So the amount of energy I have to add to undergo a phase change is given by this guy. This is my latent heat. Times the mass. So more mass means I need to undergo, I need more heat to convert that mass from one phase to another. Let me box this off. Now this formula will work for all different phase changes. So I could have the heat of vaporization here, going from a liquid to a gas. I could have the heat of fusion, the amount of heat it takes to go from a solid to a liquid. These are not the only phase changes we have. I could go from a gas to a plasma, which is a state of matter where the individual ions start to separate. I could go from one solid form to another solid form, so different crystal structures. So I could go from a body-centered cubic crystal to a face-centered cubic crystal. Water itself has, I forget the number, but some large number of different crystal structures that it can change phase between depending on the pressure, temperature, and other thermodynamic variables. Other more exotic phase changes. We could go from magnetic to not magnetic. We could go from conducting to superconducting. We could go from fluid to superfluid. A lot of different phases of matter exist. Just the solid, liquid, and gas is really only the tip of the iceberg here. Phase transitions are a huge part of physics that describe a wide variety of different fields. Everything from biology to chemistry to what stars are made of is governed by phase transitions. The last thing that can happen as you heat an object up is it'll start to glow. Here, I have your regular run-of-the-mill toaster. We're going to see what happens inside when I turn this toaster on. So here we are, got my toaster, looking inside. I'm just going to turn this bad boy on. And you can see the way a toaster works is that the electrical wires are passing current through them. They're getting so hot that they start to light up. This is a phenomenon called blackbody radiation. The wires tend to be pretty black. When I heat them up, they start to radiate light. As soon as I turn it off, you can see the current goes away, the wire starts to cool off, and I stop emitting radiation that I can see. So, how exactly does blackbody radiation work? Well, here's my blackbody. It's at some temperature T, some finite temperature. It's giving off thermal radiation. As you can see here, it's starting to glow. I can see that. So if it's giving off thermal radiation, I know I can write that as some form of heat. So we're going to call that delta Q. Delta Q is the amount of heat given off by my blackbody. Now, it's constantly giving off thermal radiation. So if I wait twice as long, I should get twice as much heat. So it should be dependent on the amount of time that I wait. I will call that delta T. Delta T is the amount of time I wait. So if I wait twice as much time, I should get twice as much heat. Furthermore, if I have a bigger blackbody, I should give off more thermal radiation. Something the size of the sun is going to give off more thermal radiation than a small ball that might be at the same temperature but doesn't have as much surface area to give off as much light. So the next thing I want to put in here is the surface area A. So I've got my how much time I wait, surface area A. The next thing is not so trivial to figure out. So this is a pretty hard derivation. I'm not going to do the full derivation here. But we'd expect that it also depends on the temperature. So hotter objects we expect to give off more heat. Well, that's certainly true. But the weird thing is it's actually temperature to the fourth power. Figuring out where that fourth power comes from is a little bit difficult. Again, not going to derive it here. You need quantum mechanics for that. We'll save that for another day. So I've got, depends on the temperature to the fourth power, the surface area of the object, delta T, the time that I wait. There's another thing I'm going to put in here. That's called sigma. That's the Greek letter sigma. This is a constant. This is the Stefan Boltzmann constant. It is equal to 5.67 times 10 to the minus 8 watts meters squared Kelvin to the fourth. Okay, so you're going to want to write that constant down. That's an important one. Now this formula by itself is the amount of heat given off by a perfect black body. So a perfect black body is something that absorbs all radiation and emits all radiation. Now, nothing in the real world is perfect. So I could have things that are 99.99999% black body, but nothing is completely 100% black body. So to take that into account, we have this constant here, which tells me what percentage of a black body am I. Am I 100% black body? Am I 99% black body? Am I 30% black body? This is called the emissivity. The emissivity is 1 for a perfect black body, 0 for something that doesn't act like a black body at all, and any number in between 0 and 1 to tell me how much of a black body this is. So here's my formula. Now, if you look at that formula for a little bit, you should something should start to bother you. So here you can see I've got temperature to the fourth power, but that's got to be temperature measured in Kelvin. So in order for me not to be emitting any heat in the form of thermal radiation, I need that temperature to be 0. Okay, let's think about what that means. I need to be at absolute 0 to not be glowing. Well, that's a little weird, right? Nothing in this room is at absolute 0, and none of it's glowing. If I turn the lights off, I'm at 98.6 degrees Fahrenheit. The room temperature is around 298 Kelvin. 298 is very different than 0. Why is nothing in the room glowing? Turns out it is glowing. It's just not glowing in the visible. So in order to see it glow, we would need to go into the infrared range. So to see things glow, to see things glowing in the visible range, turns out you need the temperature to be much, much hotter. So what we can see, if I look at the spectrum of a black body, the spectrum changes as I change the temperature. As I increase the temperature, we can see that the energy density, the amount of energy stored in the light, starts to increase. Increases at higher temperature. Furthermore, the peak in the energy density moves to larger and larger frequencies. If I look at the right, we can see that corresponds to a shift in the color of the black body. We can see that at low temperatures, I get no visible light. But then I start to get red and yellow, and then eventually the color shifts over to white. Where do I get the maximum peak in my radiation spectrum for a black body? Well, there's a nice formula that we can write down. So this is the peak wavelength that we get. If I want to see something in the visible range, we want that to be between about 400 and 700 nanometers. And my actual peak in nanometers is going to be given by 2.90 times 10 to the 6th nanometer Kelvin divided by your temperature in Kelvin. So this formula tells me what color my black body is going to look. Again, it's just dependent on the temperature. This is again, a fairly difficult equation to derive. We're just going to take it as an experimental fact. If you want to see how this is derived, just got to take quantum mechanics or modern physics, and we'll go over it.